Hello everyone. My name is Dr. Ranjith Kumar. I'm working as a associate professor in Electrical and Electronics Engineering Department, Institute of Aeronautical Engineering, Hyderabad. Then the first topic that we are going to discuss is the single phase half wave controlled rectifier with R load. So this is the schematic diagram of the single phase half wave controlled rectifier. So here we have used only one thyristor, and the input is the AC supply, which we are considering as a Vs, which is equal to Vm sin omega t, and here load, which is the resistive load. Then before going to discuss about the operation, let me show you the output waveforms. So based on output, by using these output waveforms, so we can able to understand the operation of this single phase half wave controlled rectifier. So initially we are giving the supply. Okay. So as we know here, the AC voltage supply will having both the positive half cycle and the negative half cycle for the full cycle, which is 0 to 2 pi. So here we are having only one thyristor. Then initially when we start giving the supply, the input supply here, which means we are applied a positive voltage across the thyristor, which is the anode is positive with respect to the cathode. That's what we have applied. You can see here the positive and the negative. But still the thyristor is not in a conduction mode, even though if you are giving the positive voltage across the thyristor with respect to the cathode, which is anode is positive and cathode is negative. After some delay, we are giving the firing pulses. Okay, the delay angle is, we are call it as a alpha, which is the firing angle. So we are giving a pulse or trigger the thyristor. Then the thyristor starts conducting, so that we will get the output voltage and output current. And the output voltage and output current will follow the supply. Here you can see up to alpha, here there is no output voltage and output current, because still the thyristor is in the off state. When we are giving the firing angle at alpha, then the thyristor starts conducting. Then we are getting the output voltage and the current, which is followed by the source voltage. Then up to, here the commutation that is used as the line commutation, because as we know already, the line commutation, which is also called as the natural commutation, because here the nature of the AC voltage here up to pi degrees it is the positive cycle, and after pi to 2 pi it is a negative cycle, which means automatically after the pi degrees, okay, or after the pi, the voltage across the thyristor will get reverse biased, so that the thyristor stop conducting. That's why here you can see we are getting the output voltage from alpha to pi only. But after pi, here the output voltage is 0, and as well as the output current is also 0, because the thyristor is in the off state due to the natural commutation. Then again after 2 pi, again we are getting the positive cycle, then which is nothing but the positive voltage will apply across the thyristor, but still it is not in a conduction mode, because we didn't give the firing signal or the firing pulses. Then again after the pi, we are given the firing pulse, then again the thyristor will start conducting. Then we will get the voltage, output voltage and current, which is followed by the source voltage. This is how the operation, which means during the positive half cycle, okay, here the load current will flow in this direction. This way. I naught. And during the negative off cycle, here, because during the positive off cycle, here the anode is positive and the cathode is negative, or the anode is positive with respect to the cathode. But during the negative off cycle, this will be negative and this will be positive. So which means the reverse bias applied across the thyristor, so that the thyristor will get into the off state. That's why here we are getting the output voltage and output current during the positive off cycle only. During the negative off cycle, because the thyristor is in the off state, so that we won't get the output voltage and the output current. That's why this is a single phase off wave control, which means only during the positive off cycle that we can control, but during the negative off cycle we cannot control, because we are getting the output voltage and current as 0. Right. So based on the firing angle, we can control the output voltage and current, the average RMS output voltage and current, that we will discuss. Then how to derive the average load voltage and average load current. So as we know, because for this particular waveform, here you can see the V0 and I0 waveforms are similar with each other, because here you can see Vm sin omega t, okay, and this current is Vm by R, Vm sin omega t by R. So because these two waveforms are followed by the input waveform, which is sine wave. So that's why, as we know how to find the average value of the sine wave, which is the general formula, just I am here writing, that is, let me consider E average, which is equal to 1 by T integral 0 to T, because the sine wave that we are representing as a Vm sin omega t into d omega t. This is the general equation to find the average value of a sine wave. So here we should identify what is this t and this t. This t and this t are not same, because this t is the total time period and this t is only the conduction time period. Then first we should identify what is the total time period and what is the conduction time period. Then again, let me go for the output waveform. Here, if you see the total time period, which is 2 pi, 0 to 2 pi, because if you see, if you consider 0 to 2 pi, then again 2 pi to 4 pi, the waveform is symmetrical. Otherwise, if you consider only 0 to pi and pi to 2 pi, see here 0 to pi, you are getting some conduction period, but pi to 2 pi it is 0. So these are not symmetrical, the 0 to pi and pi to 2 pi. But if you consider 0 to 2 pi and 2 pi to 4 pi, these are symmetrical. So which means the total time period is 0 to 2 pi, which means after every 2 pi, the thyristor will get conduct. Like here you can see, this is alpha to 2 pi plus alpha. I mean, it is first the thyristor is conducting at alpha, then after again it will conduct 2 pi plus alpha. So then the total time period is 2 pi plus alpha minus alpha, that is 2 pi plus alpha minus alpha, then which is equal to 2 pi. So then the total time period here t is equal to 2 pi. Then what about the conduction period? The conduction period is only here from alpha to pi, not 0 to pi, because from 0 to alpha there is no conduction here. You can see the output voltage and current are 0. So anyway, here we are going to find the average load voltage. So that's why we should consider only the output voltage waveform. So here from 0 to alpha, the output voltage is 0. It will start conducting from alpha to pi. So that's why here we should take this t as a 2 pi and this t as a pi, because, and here it is not from 0, because here it is from alpha to pi. The same equation you can see here, the EDC, which is equal to, because anyway the output voltage is DC, so 1 by 2 pi integral alpha to pi, because here the output, the output voltage that we are getting from alpha to pi only. So alpha to pi Em sin omega t into d omega t. Then you can just apply the integral to the sin omega t, then apply the limits. Here you can see the sin omega t, which is the integral of sin omega t is minus cos omega t, and then you can substitute now the limits which are from alpha to pi, then you will get EDC is equal to Em by 2 pi into 1 plus cos alpha. This is the standard equation, so everybody should remember this one. What is the average load voltage of a single phase half wave controlled rectifier with R load, which is EDC is equal to Em by 2 pi into 1 plus cos alpha. So here if you see how we can, because as we know, as we say or as we consider, this is a half controlled rectifier or half wave controlled rectifier. So which means we can control. Okay, output can be controllable. Of course, some extent we can controllable. Then what is the key parameter here is alpha, because Em which is constant and 2 pi which is constant, only the variable is alpha. So by changing the alpha value, we can control the output voltage. We can consider, if we consider 30 degrees, then we will get some value of the, what is that, the average load voltage. And if you consider alpha is equal to 60, then the value will change. So like this we can control the output voltage. Next, the average load current. As we know already, the average load voltage. So then we can just EDC by R, then you will get average load current, which is Em by 2 pi into R into 1 plus cos alpha. So this is the average load current. Like that, we should derive the average load voltage and the average load current. So here the basic thing is, this is the basic equation. If you remember this basic equation, then you can easily solve the average load voltage and the average load current by deriving this. These are simple integration. Okay, if you just apply the simple integration and substitute the limits, then you will get the average load voltage and as well as the average load current. Then how to find the RMS load voltage? Then again from the standard equation in case of RMS voltage of a sine wave. So let me consider if it is a voltage VRMS, which is equal to again 1 by T. Here first let me go for the equation. So here 1 by T into integral, again it is from 0 to T, again here it is Vm sine omega T whole square into d omega T, and we should give the root, because the root means square RMS value. This is the standard equation. Again in this case we have to identify what is the total time period and what is the conduction period. The conduction period, it is from alpha to 0 to T usually we consider, because this is a this for the sine wave. But anyway, here for the load voltage already we have identified the total time period and as well as the limits. The total time period here it is 2 pi and the limits are from alpha to pi. The same things here I have substituted. You can see 1 by 2 pi in the place of T I have substituted 2 pi, and the limits of the integral is alpha to pi, then Em sine omega T whole square into d omega T. Then again you can just simplify this equation, then we will get the RMS load voltage. Here I have taken Em square as a just because Em square is a constant, only here the integral that we can apply to the sine square omega T into d omega T. So here the sine square omega T we can write it as a 1 minus cos 2 omega T by 2. Then apply the integral for the 1 minus cos 2 omega T by 2. Then if you apply the integral, then here the integral of 1 into d omega T will become omega T, and the integral of cos 2 omega T will become sine 2 omega T by 2. Then apply or substitute the limits which are alpha and pi. Then finally you will get the ERMS, which is equal to Em into pi minus alpha by 4 pi plus sine 2 alpha by 8 pi and whole to the power of 1 by 2. This is your the standard. Yeah. So this is the final RMS equation. This is also everybody should remember what is the RMS value or what is the RMS equation of the load voltage in case of single phase half wave controlled rectifier with R load. That is ERMS is equal to Em by 2 root pi into pi minus alpha plus sine 2 alpha by 2 whole to the power of 1 by 2. Similarly, we can find R as we know here alpha is the key parameter to change the output voltage and current. So suppose if the firing angle alpha is equal to 0, then we will get the maximum RMS voltage, which is ERMS is equal to Em by 2. Because if you substitute alpha is equal to 0, okay, then here the pi gets cancelled. Then here alpha is 0, okay, and sine 0 is equal to 0. So 0 by something 0. Then the total term inside the square root, okay, will be having only the root pi. Then the root pi will get cancelled. Then we will be get, because here you can see this term will be get 0 and this term will be get 0. And here this term will become root pi and the root pi will get cancelled. Then you will get only Em by 2. Like that, the RMS value will depends on the alpha value. Then the RMS load current. Similarly, like RMS load voltage, already we know what is RMS load voltage. Then just ERMS by R, then you will get the RMS load current. Okay, so that's how we can derive the RMS, the average load voltage and current as well as the RMS load voltage and current. Next, the power delivered to the load. So there is a DC and AC powers. The input is AC power and output is the DC power. So suppose if you want to find the PDC, then it is EDC into I. Already we know what is EDC and IDC. Just now we have derived. Then you can substitute EDC and IDC here. Then you will get the PDC. And similarly PAC, that is RMS load voltage into RMS load current. Okay, so just now we have derived the RMS load voltage and current. You can just substitute the ERMS and IRMS. Then you will get the PAC, that is IM square, IRMS square into R. So similarly, the input VA, that is RMS source voltage into total RMS line current. Okay, then you can substitute these two values. Then you will get the total input VA, which is root 2 into ES square by 2 into R into root pi into pi minus alpha plus 1 by 2 sine 2 alpha whole square. And we can also find the power factor by using this equation, because these all are the standard equation that you know already. These are all the parameters like the power delivered to the load and input VA and the power factor. If you want to find all these parameters, before that you should find the average load voltage and current as well as the RMS load voltage and current. Then the power factor, which is equal to, if you substitute the power delivered to the load and input VA, then you will get the power factor which is equal to ERMS by ES. Because here IRMS will get cancelled, then you will get ERMS by E. This is the power factor in case of the single phase half wave controlled rectifier with R load. Similarly, we can also, or if you substitute the ERMS and the ES value, then you will get the final equation for the power factor, which is this one. Then the efficiency PDC by PAC, that is output by input. Here output is PDC and input is PAC. So just now we have here calculated this is PDC and this is PAC. Then you can substitute, then you will get the efficiency. Similarly, the ripple factor, that is ERMS by EDC. Okay, so like that we can find the different parameters based on the average load voltage and current as well as the RMS load voltage and current. This is how we can find. So this procedure, whatever the procedure we have followed to find the average load voltage current and as well as the RMS load voltage and current, the same procedure that we can follow for other types of rectifiers also. Like next we are going to discuss about the single phase half controlled rectifier with RL load. So for the RL load also the same procedure. Here the key parameters are that we have to identify what is the total time period and as well as what is the conduction period. These are the only the two key parameters. So based on these two key parameters, so we can derive the average load voltage current as well as the RMS load voltage and current. Next, the single phase half wave rectifier with RL load. See, then when coming to the output waveform, just you have to compare with the single phase half wave rectifier with R load. Okay, so which means here we should find what is the effect of these inductance or effect of this inductor. If you see the output waveform, of course the procedure is same, the operating procedure, right? So here initially we are giving the positive anode voltage with respect to the cathode, and at alpha or after firing at alpha degrees we are giving the firing pulses to the thyristor, then the thyristor will get turned on. But before, as you can see here, in case of R load, the output voltage waveform is this is 0, pi, 2 pi, like this we got the output voltage waveform, and as well as the current also we got same waveform, similar like the output voltage. So which means when the thyristor will get turned on at alpha degrees, so the current is rising very rapidly and it is following the input voltage or input waveform. But in case of RL load, here you can see when the thyristor is turned on, still the current is 0 and it is gradually increasing. Okay, and even though at pi, okay, still the current is flowing through the load, but it becomes 0 when it reaches to the beta. Why here it is not rise rapidly like in case of R load? Because here the basic property of the inductor. The basic property of the inductor is it does not allow sudden change in the current. So that's why here it is gradually increasing. Okay, and after it reaches to the peak value, then it is gradually decreasing and it will become 0 at beta. Then when coming to the load voltage waveform, anyway from alpha to pi it is similar to the voltage waveform which we got in case of R load. But here we are getting a small amount of negative voltage from pi to beta, because this is initially when we are giving the firing angle alpha, then the current will flow in this direction. So which means then the inductor terminals are like this, plus and minus. So during the thyristor T1 is conducting, the inductor will store the energy. So when the thyristor terminal will get reverse, then here the inductor will start to discharge by changing its terminals as a negative and positive. Then it will discharge through the it will discharge the energy, but still in this case also the thyristor will get into the turn on position. So that's why here we are getting some load current from alpha to beta. Okay, so then in this case the conduction period is alpha to beta, not alpha to pi, because even though some some duration from pi to beta, still the thyristor is in the conduction mode. When it reaches to the beta, then the thyristor will stop conducting. Then the load voltage and the current will become 0. That's what here you can see by this VT. This is the terminal voltage across the thyristor. So from 0 to alpha, thyristor is in the off state. So that's why we are having a small voltage across the thyristor. And again here from alpha to beta, so there is no voltage across the thyristor because it is in a conduction mode. So that's why here the voltage across the thyristor will become 0. Then after beta again the voltage across the thyristor will follow the same source voltage which we are applying. This is the operation of the single phase half wave rectifier with R load. So then this is the effect of the inductance in the load. We are getting a small negative voltage, and as well as we are getting the conduction period also increased, because before it was 0 to pi, alpha to pi, but here it is alpha to beta. Then here you can see there are three different angles. One is alpha and beta and gamma. So here already we know alpha is the firing angle, and here the beta is called as a extension angle, because the conduction period is extended from pi to beta. That is, the beta is called as a extension angle, and then the gamma is called as the conduction angle. The gamma here you can see from alpha to beta, the duration is called as a gamma, so that is the conduction angle. And the extension angle is not from pi to beta, okay, that you should observe here, from 0 to beta. This is called as the extension angle. This duration is called extension angle. And alpha is only this duration from 0 to up to this point. This is the firing angle. Then in this case also, we can derive the average load voltage and the average load current. Similarly, here the same equation we are using, but only the change is here the conduction time. The conduction time in this case is alpha to beta, and here the total time period again 2 pi, similar like in case of R load. Then apply the integral, then substitute the limits, then you will get EDC is equal to EM by 2 pi into cos alpha minus cos beta. Before it was EM by 2 pi into 1 plus cos alpha. Here it is EM by 2 pi into cos alpha minus cos beta. That's what here the output load voltage will also change with respect to the load also. Then similarly, the average load current, already we derived the average load voltage, then EDC by R, then you will get the average load current. Similarly, the RMS load voltage, here the same equation, you can just apply the integral and substitute the limits, then you will get the RMS load voltage, which is equal to EM by 2 pi into beta minus alpha minus 1 by 2 into sine 2 beta minus sine 2 alpha whole square. The similar way you can also find the efficiency and as well as the power factor, okay, and as well as the ripple factor, similar like in the previous case. The basic thing is you have to find the RMS load voltage and RMS load current. The next topic is the same half wave rectifier with RL load and freewheeling diode. So what is the effect of freewheeling diode, that we will discuss in the next class, and thank you.
Like, share and subscribe. Hit the bell icon for more updates.